Good morning, everyone. So I'll start off by saying my name is Nelson Jurado. I just graduated from my undergrad this past December from UC Berkeley and will be attending UC San Diego this fall for my master's in structural engineering. And today's presentation will be on the effects of calcium sulfoaluminate, or CSA, on limestone calcined clay cement, or LC3, performance for 3D printable concrete applications. So I want to start off by saying that the construction industry as a whole is shifting more towards sustainable practices, and one of the biggest practices that's taking off is 3D printable concrete, right? 3D printing structures to make them more material efficient, to have greater design flexibility. All of these factors are beneficial. However, there is the unfortunate side effect of these structures being highly reliant on high cement content mixtures due to the fact that during the extrusion process, you actually have, you're not really able to use coarse aggregate. So to counteract this fact, we explored the LC3 system, which would allow for up to 50% replacement of the cement content. So we looked at a Ohio-based clay, which showed comparable long-term or 90-day compressive strength or mechanical properties to PLC as our specific specimen type. But what we noticed was that at early age, for this specific type of clay, it actually has slower setting binder at early age. So if you think about 3D printable concrete and the supporting, of the layering process, it's very important to control your early age rheology and setting time. So we also then explored CSA for its fast setting properties, in which you could actually see it literally set in your hand if you held it for only a few minutes. So our aim was to conduct a set of experiments which would accelerate concrete early age setting time and enable the prediction of vertical support for 3D printed concrete layers. And we also wanted to evaluate the strength gain of up to just past final set. We also wanted to evaluate compressive stress up to 7 days while varying the levels of calcium sulfoaluminate. Now, and finally also to utilize heat release as a measure to evaluate early age hydration and predict concrete mechanical properties. So here you can see to your right the actual clay that we got from the Belgian brick company. It's called Fire Clay number 5, and you'll see it was calcined at 700 degrees Celsius to go from that gray to the more light brown color. You'll also see that we specifically split up our specimen into 5 distinct types with varying levels of CSA replacement. So there's the 0%, 5%, 10%, 15%, and 20% CSA replacement. Specifically in the pie chart to your left, you'll just see the 20% CSA replacement, with the remaining 80% being split amongst the LC3 system and PLC. It is also important to note that the clay was milled to similar particle size. Now, we started off by conducting our BICAT testing using ASTM standards, where we saw that there was a drastic decrease in the setting time of all 5 of our specimen as we increased the percentage of CSA replacement. So at its peak, the difference between the 0% CSA replacement or no CSA with 20% CSA replacement would be a 90% drop in setting time, which was over a 90% drop in setting time, which was really interesting to see. That's a difference between about 6.5 hours and 23 minutes. So we then went on to explore compressive stress testing by creating our 2-inch by 2-inch by 2-inch cubes, where we looked at the compressive strength at 1 day, 3 day, and 7 day periods, which we have here as the color of each line, and the axis being the compressive stress on the Y, and the actual percent CSA on the X. So you can see that the 15% CSA replacement actually performed the best in all 3 periods, 1 day, 3 day, and 7 day. But notably, there was also a decrease in compressive strength at 5% and 20% CSA replacement. One potential theory that we were considering is that at higher levels of CSA, it actually consumes a lot of the gypsum that was used within the LC3 system and makes for a more inefficient hydration process at later, yeah. So you'll see, we'll see this more in the coming slides. So I just wanted to say we also explored isothermal calorimetry for heat release analysis, and we want to point out that there are 2 distinct peaks, right? You have your first peak, which is very close to when you first insert the sample into the machine because of its sensitivity to ambient temperatures and environmental factors, which affect the results slightly, but it still shows the general trend of each of the samples that were placed within it. And the second peak, which occurs slightly afterwards, or a few hours afterwards, would actually be more viable because it has minimal environmental factors. So I want to start off by showing the cumulative heat evolved within the isothermal calorimetry. And you can clearly see that the orange line, or the 15% CSA replacement, had the highest cumulative heat evolved after 3 days, which reflects why we could see the higher compressive strength. It had more likely to have a longer amount of time hydrating at a higher rate. Now, we see that 20% CSA, there's a very steep drop off. There's a high initial acceleration. That's the light blue line, but it's very steep drop off at 25 degrees Celsius and at 35 degrees Celsius. So specifically for all our testing in lab, it was around 25 degrees Celsius when we conducted the test. So we look at the 25 degrees Celsius chart for comparison to our other results. But it's notable that 35 degrees Celsius, the 15% CSA, which was at the highest level of cumulative heat evolved, actually went down to the lowest. So temperature is a huge factor in that regard. So here, this is just the non-cumulative heat evolution of the samples, and you can see quite clearly how the 15% CSA, or the orange line, is able to maintain somewhat of a peak, even at 25 degrees Celsius, whereas the 20% CSA has a steep drop-off, along with at 35 degrees Celsius, both of them have a steep drop-off, don't appear to have a second peak, and are almost identical at 35 degrees Celsius. You can barely see the splitting of the two. So, with that being said, we then conducted a set of very early age compressive stress tests to compare the actual relationship between 2 of the factors or of the data types that we've been collecting. So we looked at cumulative heat evolved and compressive stress and looked at the relationship between the 2 and saw that there was a high correlation with R value of 0.913, and that is a strong indicator that the actual percentage of CSA, or that the percentage of CSA that's changing, because we looked at both 0% CSA and 20% CSA. So in this specific graph, you'll see that this linear regression line actually goes through all the data. So it means that despite the fact that there may be varying levels of CSA, it's still valid as a predictor of the actual mechanical properties of the concrete at early age. by that I mean the heat evolved as a predictor. And so, just to kind of summarize, we have our conclusions being that at higher CSA replacement by weight, we see a significant decrease in initial setting time, up to 90% with the 20% CSA replacement. And then at 15% CSA, which is kind of the more exciting one, you see that you can maintain a high cumulative heat evolution at 25 degrees Celsius, the highest of all of our specimens tested. You can also see that as the greatest compressive stress at 1, 3, and 7 days. You'd also see that it still has an over 80% reduction in initial setting time, and therefore kind of acts as the most viable of all our specimen tested for 3D printable concrete applications. And we also saw that there's a potential for hydration inefficiencies which occur at higher levels of CSA replacement due to its consumption of possibly gypsum and other things that we can see based on it having the lowest cumulative heat evolved at both temperature ranges and the lowest one of the lower compressive stresses compared to 15% CSA replacement. And lastly, that heat evolution and compressive stress are highly correlated regardless of CSA percentage, and this can support that heat release is acting as a viable predictor of concrete mechanical properties. So with that being said, I just want to thank my professor, Lisa Burris at The Ohio State University, where I conducted this, the National Science Foundation, and everyone else in between, and of course ACI.